Hello and welcome. Today we are going to chat with Renzo about our great success that we have reached 100 stars in GitHub in the LayNii repository. So Renzo, welcome.
Thanks. Great occasion.
So okay, then it's a bit of a random discussion that we are going to have today, but I think this might be start of maybe something funny that we can do over time. So let's maybe start very briefly introducing ourselves. Like, who are we? Like, who are you, Renzo?
I'm Renzo Huber. I'm leading the layer group at the Martinez Center for Biomedical Imaging at MGH, Harvard Medical School. And I'm an MRI physicist. I specifically focus on acquisition method development for high resolution fMRI and MRI. I invest a bit of my time also in the kind of software-wise, whereas I'm mostly focusing on acquisition. So I'm one of the co-developers of the LayNii suite.
Okay, good to know you. Well, we knew each other for a long time, but I can also briefly introduce myself. I am Ömer Faruk Gülban. I am working at Brain Innovation in Maastricht, Netherlands. And I am basically developing high-resolution MRI data analysis algorithms and implement them in different software. One of them is LayNii. And I think starting from 2019, we are working very closely together with Renzo and pursuing advancing analysis methods together, as well as the acquisition methods. But I'm maybe a bit more on the analysis side. Then Renzo is a bit more on the acquisition side, but we have this like nice balance between each other that we kind of push forward each other and then do like stuff with like high resolution MRI data and fMRI data. But by the way, like I'm just talking about it, but I assume that the audience knows what is MRI or fMRI or what is LayNii. But maybe we can briefly just talk about like what is this thing that we had 100 stars for? Like what is LayNii, Renzo?
Right. So LayNii is a collection of very lightweight C++ programs that are specifically tuned for my field of high resolution MRI or high resolution fMRI analysis. And I guess the name is the program. So Lay, the first syllable, stands for layers, representing all kind of high resolution mesoscale layers and columns. And Ni, the second syllable, is nifty, which sets kind of LayNii apart from other software suites. So I wanted to put nifty into the name because different than other softwares, LayNii really works completely in the nifty space and the voxel space. So you always have a nifty that goes in and a nifty that goes out. So even the layerification is not really based on surfaces or surface models. Everything's in nifty. I guess LayNii is mostly used for the layerification. And by layerification, I mean the process of converting kind of tissue type segmentations, basically maps that assign each voxel to either gray matter, white matter, and CSF, and take those tissue type segmentations and convert them to layers to kind of know where to expect within gray matter a certain layer to occur, layerification. However, myself uses it, and many people use it also for other things, like simple things like, for example, bold correction in blood volume sensitive vaso data that are popular at high resolutions, for specific Q&A that is unique for high resolution imaging, and basically anything that is not conveniently available in other software suites.
I see. So maybe this might be a good moment to talk a little bit about the history of LayNii. Like where did this come from and how we ended up working together? Maybe you can start with the beginning of the history of like why did you start developing all these things and implementing your own algorithms? Like why not you just used someone else's algorithm or some library out there, and where is this need coming from?
I think the first attempts were maybe 2011, 2012 or so. Very naive starts. And in those days, as many developments in I guess, in research, it came out of the kind of desperation of not having anything that works, or maybe out of the failure to reproduce what other people could be doing. So in those days, shortly before 2015, layer fMRI was getting a lot of traction because the data were getting better and better and better, and 7-Tesla was getting more established. And I saw these layer profiles being published from other folks, and I had good data, but I could not kind of convert those 3D maps into layer profiles. So that was the need. And at that time, I was a PhD student in Max Planck Institute in Leipzig in the neurophysics department headed by Bob Turner. And there were other softwares available. For example, at this time, Pierre-Louis Bassin was there. And he was under high demand. Like he had the CBS tools developed. And as always with people under high demand, he had less time that he had kind of collaboration requests. So he could kind of pick his collaborators. And it was hard for me. He referred me to one of his students who kind of failed to install the software at my computer. So it wasn't really a solution for me. So instead, I did it with Odin. Odin was a kind of nifty read-write that was very specific, only worked on one Linux version to kind of develop the very first layer verification algorithm, basically by estimating distances of voxel counts. Later, as a postdoc in Peter Bagnatini's group at NIH, I again tried to kind of find other softwares that worked for that, specifically asking Paul Taylor. This was maybe in 2015, 2016. Again, kind of they were busy and had maybe didn't really see the need for it. So they kind of deferred me to these nifty IO programs that was used in AFNI, but didn't really encourage me to implement it in AFNI itself. So I used those, which was much better than the previous version in Odin because I could compile it on Mac, on Linux, on any Linux version. It had zero kind of dependencies, which is also something that we try to maintain in the history of LayNii, to have no dependencies. Anything that we need is encapsulated. That was useful to my colleagues. Of course, there are many cool softwares out there. Every paper, I guess, develops their own little software, and some of those softwares are excellent, but very few of them really kind of make the cut to be useful to a wider field outside the group of the developers. And I think that the point that made that happen was basically when you joined that was in, you said 2019.
2019, right? I think, right? You arrived to Maastricht, I think, right, at the like beginning of 2019, maybe, if I remember correctly, in January.
Right.
Is it correct? Yeah.
I think, yes. Maybe I had a GitHub repository before. I used it like Dropbox or something. Yeah. I had no idea. You taught me how to kind of take advantage of all the features in GitHub. You kind of professionalized everything, like going through all the code, line by line by line by line, modularizing, therefore making it more stable, making it readable, which ultimately, I guess, led to the credibility that other people felt confident in using it. So I guess that was the really third attempt to get support from other softwares as well. Like you were from industry, you were working for Brain Innovation, the company behind Brain Voyager, under the umbrella of Rainer Göbel, and this was extremely helpful to have this support there. And kind of you had, I guess, hundreds of commits every year since then. It really took over most of the maintenance, including more algorithms. So I guess maybe for me, the most relevant keystones that happened after you joined was kind of the professionalization of the repository, having versions, having releases, and so on, then having kind of a modular code that worked, which made it basically usable, not only for the data that I worked with, but made it more generalizable. But then also, as a result of that, you kind of re-implemented the same algorithms and then innovated them with this kind of different ideas. For example, you wrote this completely new layerification algorithm in now the workhorse of LayNii, the LN2 layer program, and in your own way of doing equivolume imaging, which now is the most often used layerification algorithm used in the collection of human layer-dependent fMRI papers, specifically since the pandemic. So there are about 170 human layer fMRI papers published since the pandemic, and the majority, the program that is most often used is that LN2 layer programs. But also you then introduced other programs like the LN2 columns, which blew me away, kind of in the sense in opening up the kind of three-dimensional space across the cortex. And that's a program that maybe really hasn't gained a lot of traction since then, as much as, for example, the LN2 layers, but still it led to the patch flattening, the multilaterate, all these programs that are kind of being very helpful to do laminar and columnar analysis at the same time.
Maybe at this point I can just briefly tell my story about how we came out to working together, because around 2013 I was doing my master studies, And there I got introduced to high resolution fMRI at 7 Tesla and looking at layers and columns and so forth. Actually, I was looking at the motion direction columns at Human Area MT, working with Rainer Goebel and back then Valentin Kemper. And there I realized already that this is something really hard to kind of extract information out of from the data. You need to compute the layers, you need to compute other parameters, and then really like study the columns out there. So I started going into more and more how they were doing it. And of course, like Rainer Goebel is particularly an expert and one of the frontiers in this high resolution analysis software and algorithms. And I used a lot of Brain Voyager back then, which used surfaces rather than the volumes. And around the same time, I started my PhD, and there we constantly had a issue of basically computing these equi-volume layers. That was like a mystery. Like someone in Leipzig can do it in the CBS tools. Then we were trying to understand how it is used. Again, similar to you, I had very similar problems like installing CBS tools. At the end, we managed, but it took like months basically to install, then to figure out how to run equi-volume layers and so forth. So when we came together in 2019, that was the last year of my PhD, I was already at a point in my like daily research that I was kind of tired of it. Like I knew how to compute the layers and columns and so forth using these triangular meshes and so forth. I kind of figured out how to use CBS tools, but I felt that it should be easier. Like I want to do other things with my data, not spending all the time trying to compute those things. And also like teaching other people to do those things was a challenge for me. And then you came to Masri, then the pandemic happened as well. We should highlight the role of pandemic because we had like not much to do. I remember you and we were going to the department, one of the few people that still went there and like be in separate rooms, of course. But around that time, I really had like nothing else to do. Then I start looking into C++, your code, and start developing things. And I think it's funny that maybe like pandemic actually helped us to eventually like put LayNii as a like actual software package. And I remember that you were at the beginning thinking, oh, well, it works for me. I can do my analysis. I don't need to do more than this. Like I can teach some people around me. And whereas I think then we decided to push forward for making a software package out of it, a bit more like putting it nicely together and then eventually writing a paper, right?
Sure, I think you were the driving force. Indeed, I didn't really see the need for the paper. I was happy enough that I have something that works. I do appreciate those kind of this game of collaborating, which is very, very rare. And maybe I've never had since then that kind of I was doing something, you were doing something, and then kind of it was really building something that was exciting. Yeah, the pandemic, I guess, kind of many people suffered a lot from it. For me, it was kind of something that cleared my workspace. It was also the time my family grew. So I was limited by time, and so it kind of helped not being allowed to scan and not doing lesson meetings and just focusing on kind of the code in front of me.
That was an exciting time in a way. Okay, so let's stop for a second, Renzo, because we can, I think, reminisce for hours about how we like ended up working on LayNii together and our adventures. Maybe we can save it for like later chats. But I am curious because like once you have a large user base, people sometimes misunderstand like some things or use them incorrectly or in the wrong cases. So what do you think are the three largest misconceptions about LayNii that you encounter?
There are many, yes. Specifically, kind of you taught me on GitHub how to use the issue page, which is basically this forum where users can do kind of ask user-initiated questions. And we have about 100 or 97 topics there already. And there are common themes that kind of users don't fully kind of capture, even though it is in every kind of introduction and manual in there. Maybe the first thing is that a feature of the fact that LayNii works in voxel space. So it estimates layers in voxels. So basically, the underlying spatial grid determines the accuracy of the layers. So we do recommend that you apply LayNii and the layerification at a spatial grid that is finer than your layers. Basically, when your experimental data are just barely enough to see layers to begin with, like 0.8 millimeter resolution, the resulting layers on that native resolution might work, but they're not the best. So one thing that I keep repeating over and over and over again is to apply the layerification at a fine spatial grid, even if it might mean that you need to upsample your data and then might need a bit more memory for that.
Yeah, this also reminds me like why people did use the surfaces back in the day, like in Brainwager for us, or also other software like FreeSurfer and so on. Because when you switch to the surface representation of the data, you can operate in a finer grid to compute things. Whereas, and maybe that's better for when you have 0.8, 1 millimeter data and you don't want to upsample anything and so forth. But like the most common misconception that I encounter when maybe others use or talk about these things is like they ask, oh, which one is better? Which one is better? Well, I mean, the like there are algorithms that try to implement some ideas, like how you compute things that are related to the geometry of the cortex. And each algorithm has advantages and disadvantages, right? And what to me unique in LayNii is that principle that we always stay in the voxel space. So there is like some easiness there, but it also means that, of course, if your discrete steps are too few in between two boundaries of the gray matter, you will just compute things in a more error-prone way. Like you will overestimate or underestimate. Whereas if you switch to a more finer representation like the surfaces, you might do better. Though like it doesn't mean that like surfaces are just better, because you are changing the representation and you are kind of creating a fine resolution where you don't have it in the data. So one has to be like really careful. And if you are not really into the algorithmic details of how these things are implemented, I think one should refrain from saying that, oh, I use LayNii is the best, or I use surfaces in this and that software is the best. I think that's like the wrong way of looking at it. But to go into detail, you need to really get your hands dirty with the algorithm. And there, like LayNii is useful because it's all open source, right? You can really open the code and read exactly how we compute it.
Right. And maybe another kind of angle of the surfaces versus voxels is that kind of very often as an acquisition focused person like myself, I have messy data, right? Yes, I'm interested in the brain, which has a nice topology of closed surfaces without holes. My data are not fulfilling those requirements, right? Very often I have SLAT data, and I would like to just quick and dirty see the layers within my SLAT API data, without being limited by the questionable accuracy of distortion correction or alignment to an anatomical template space or something. So LayNii can basically, because it's not using surfaces, can work in any kind of space you want. And then we do see very funny applications of LayNii in something like doing layers in brainstem or cuniculi or cerebellum, or even just taking a screenshot of a paper and then doing two-dimensional layers of the gray values of that screenshot. So kind of it's just a different niche, a different realm of where you can apply like voxel-based or not kind of vertex-based layerification algorithms.
Yeah, indeed. And that's actually a point that we should emphasize. Like for me, like what was really the killer application of LayNii is the partial coverage data. When you have small slabs, as you can have in the high-res anatomical, I mostly do anatomical imaging, so I'm more interested in that. But in either case, like when you have smaller slabs with high resolution, sometimes you just want to simplify things and you don't want to acquire like whole brain. I just want to analyze my data there in that small slab, right? And like for instance, I also work on the postmortem data, and sometimes there are just brain chunks that are imaged. There's not even a whole brain to use. Therefore, I use LayNii quite a bit in those type of data. Even as you said, like getting some pictures from old books, putting layers quickly, and then trying to basically understand what those old pictures meant with regards to when you apply equivolume or equidistant layering and so forth. So it is like we should emphasize that really like we are not talking about whole brain standard type of data. We are talking about very much specialized, like small coverage, advanced, and many times messy type of data. Okay, so maybe, I mean, there are so many misconceptions, I feel. Do you have anything else to kind of highlight? I mean, also, like, I don't want to be too negative, like saying people are, there are of course, like there will be misconceptions. These are complicated things, and sometimes you just want to analyze your data and be done with it. Like you don't want to get nitty-gritty with the algorithmic details of this and that. You just want to run something. Here are the layers, and here is my p-values, whatever, and then you want to rush to the paper, right? So it's okay, but this is exactly why we are also doing this conversation, because hopefully, like together with our documentation, with our YouTube channels and explaining things and now discussing about it, if anyone is interested to listen to it, hopefully you will understand like more in detail, like how these things are being done.
Some of the misconceptions come from just being false advertisement and I guess over enthusiasm, like people who say, yeah, it's the best. And it kind of course, it's not the best. It's just a different niche, I guess, for applications. But one thing that I often struggle with is that kind of to make the point that LayNii is not providing tissue type segmentation. It uses tissue type segmentation to convert them. You're laughing, to convert them to layers, right? But and LayNii kind of interacts with other software suites that provide tissue type segmentations that can then be manually edited or not. But at the end, LayNii uses tissue type segmentation and estimates the layers based on that. And if you have low quality tissue type segmentation, the layer estimates will also be low quality.
If your input is flawed, we cannot save you. Okay, like after this section, I want to ask you, Renzo, what is the current state of LayNii?
Maybe that's a question that you can answer better. So right now I do see kind of new things being developed and other things being deprecated. Maybe the big new exciting thing is there are new features, like there's the LayNii, which you might introduce in a second. There is also a change in the overall, I guess, governance structure that kind of I'm commuting less and less. You took over also the maintenance, and I'm still including kind of programs here and there. For example, and currently, the last commit maybe from last month was something on artifact mitigation and Frisco to kind of really push the acquisition to high and high resolution to go to 0.35 millimeter, for example, which is limited by artifacts, but then there are LayNii programs that try to capture those artifacts and remove them. I do see that other programs that were very popular are kind of being less used. For example, something like the LN2 layer smooth, where you can smooth within the layers without signature leakage across the layers. And that was something very popular just a few years ago. And maybe now, because of the Nordic denoising, it's not really being used so much. And also smoothing is something that people are always kind of allergic to when it comes to high resolution, even though it's spatially informed smoothing. Other things that were popular and used in a handful of exploratory studies is the deveining, basically using deconvolution models like the LN2 devein that tries to use grain echo bold data and then use knowledge of the underlying angio architecture to get rid of the venous contamination in bold. That was something that was popular and has not really caught on as a method, I think, and therefore also not as a LayNii program and so far.
Yeah, I see. From my perspective, I am more and more using LN2 columns and LN2 multilaterate program together with the LN2 patch flatten. These are the things that I have actually developed in these pandemic times, kind of preparing for the future data acquisitions that I wish to have. And luckily, like those days are here. Now we can get robustly like 0.35 millimeter, for instance, whole brain human data, in vivo data. And there, the problem is usually you have so much resolution that you might want to just focus area by area rather than trying to do something with the whole brain at the same time. And those tools, these LN2 columns, LN2 multilaterate, LN2 patch flatten, these are really designed for like selecting patch of cortex and then really studying it in detail, flattening it, projecting some values within that, and measuring things like curvature, thickness, and some other properties there. So I am using this part more and more. And I think what will come out is that I will be working on more, I think, papers that actually use these tools. Today, I think maybe like 2 or 3 papers use those. One of them is actually our hand dystonia paper. I think that was the first application of the LN2 multilaterate, that we like flattened like a little piece of the motor cortex and looked at the finger maps there. And yeah, like the other thing that is going on is this LayNii that is a GUI. So we are kind of venturing into GUI business. And maybe like that we can talk about it on another time. This is very much in an early stage. So I think maybe it doesn't make sense to talk about it right now.
One further direction that I see kind of evolving and getting more traction is also kind of combining LayNii with other software suites. Like, for example, the APNI team, right? They wanted to hire you as a staff scientist to kind of use that skill, include it into APNI, if there wouldn't have been this kind of change in administration in the week before you're hiring. But also Marco Barilari, right? He invested several months in his Layer fMRI toolbox, which is basically a pipeline combining free surfer segmentation outputs to pump them through LayNii in a kind of convenient fashion to have this translation between the vertices and the segmentation from the vertices into the voxel space of LayNii, which is also something that I see. And you being kind of 100% employed by Brain Innovation, the Brain Voyager company, also means that kind of there are opportunities to put aspects of LayNii into plugins of Brain Voyager. So I do think that sooner or later this development will like go on, and LayNii will be more integrated and interacting with other software suites more and more.
Yeah, actually, just this week, I think Rainer was working on exactly this, to call LayNii and then integrate some outputs from LayNii directly into Brain Voyager. I think he will talk more about it soon in the CMRR workshop that is coming, I guess, next month.
Yes.
So just for anyone wondering more in detail about what is this LayNii, what are we talking about? Like, what would be the one that like a one source that they can go and read about it, Renzo?
So the main hub and the mother page that refers to everything that's out there is the GitHub page, which is github.com/layerfMRI in one word. And there's the LayNii repository, and on the LayNii README page, the homepage of the LayNii suite, there are a lot of links to other things that you might care about. For example, there are blog posts that go through the details and the nerdy aspects and maybe some kind of funny, more entertaining aspects of each individual programs, which is on layerfMRI.com, the website, but also Things on Things, the blog from you, Farouk.
Oh, that's my blog, yes.
But then also there are kind of many YouTube videos. For example, you have this series of kind of helping people with their specific data set, which very often calls LayNii. You kind of show in practice how you would apply it on a given data set in combination with other Python tools that you're using. All of those resources, including the paper that describes it on a kind of bird's eye view scientific level, are referred to from the GitHub page, which is github.com/layerfMRI/LayNii.
Yes, that's right. And I remember that we had this recent book chapter that we wrote together last year. If someone really wants to read a bit more academically written text, I would say, and not blog posts and YouTube videos and so forth, maybe they can read that one as well. Okay, well, let's not overstay our welcome, Renzo, and talk about this strange and niche stuff for hours. Maybe we can do it over time. What do you think? Like, I don't know who would listen, honestly, this type of conversation, but I kind of have fun anyway.
Yeah, it makes sense. I think that there would be need and interest to specifically go into details of certain applications. For example, along the lines of tutorials, like having a reference data set and then pumping it through the entire layerification analysis change. Those would be things that we could talk about, or also kind of other kind of user-initiated topics that would be of interest.
Yeah, I guess, for instance, maybe you can just show how you use it in one meeting that we have, and maybe I can show some other parts, because like why we are doing this, to me, is like there are things that is just not really possible to write in a paper, or maybe not even a blog post. Like there are some things you just need to get the data, look at it in some software, look around, and then really show people like what is happening, in our daily life as a scientist and researcher. I want to make that clearer.
Yes.
Well, then, thanks for the time today, Renzo, and maybe see you in the next one.
Thanks for having me.
Or in the next 100 stars.